Okay. Um, so the next question that we will be solving is binary tree paths. Now, what is this question? So this question is simply, let's say, DFS, in the sense that this question wants us to find all the paths that start from root of the tree and go all the way down to the leaf, right? Now, this is what is known as DFS, which is depth first search, which basically means that you start from an origin and you go till the very end, till the leaf node has arrived, till there is no other path to take. And let's say we take this example 1, 2, 5, and 3. Uh, 1, 2, 5, and 3. Now, from a very common sense point of view, we can see that there are two paths in this particular binary tree. We have 1 to 2, 2 to 5, and 1 to 3. And there is another example in this question, which is basically just a root 1. Now, for this, the only path possible is 1. Now, we can intuitively see what we are expected from this problem, what is expected from us by this problem. Um, but how do we solve this is the question here. Not that if we understand it or not, we can simply see that all this question wants us to do is just to find out the paths from the root till the leaf nodes and find all such paths and put them into a vector of string with arrows the way I have written over here. If there is no other node after the root, you will not see any arrow, so you will have to handle this case also. So how do we solve this problem? So the algorithm for this problem, um, so first of all, let's talk about the base case. Here, the base case would be if for that particular scenario where we do not have any root, right? So in the case of not having any root, what do? We do not do anything. We do not call anything. We do not do any processing. We simply will return our vector. So we'll have to first initialize an empty vector of string, and if there are no roots, then it simply means there will not be any path, and hence we can simply return the empty vector. Now about this is all about the edge case, or this particular scenario where we do not have the root. What about other cases where we have a single root or like a proper binary tree? So how do we solve that? So for that, we will have to keep track of two things. Um, First of all, the vector that we have initialized, right? So it should contain, it should have all the paths. So when I am doing the recursion, when I am uh, traversing through the tree, I will have to keep track of the paths that I have encountered. If I arrive at at the end of any path, I have to store it at that particular moment only into the vector, and also keep track of where I am in that tree. So where exactly I am in that hierarchy, we also have to track. So from that, we realize that we need two things to be tracked. We have to track two things here. First, the path that we have traversed up until a certain point, and all the paths that are complete. So what do I mean by that? So say I start from one. As I said, this is a depth first thing, which basically means that I'll go do uh, all the depth first instead of doing a level order traverse. In the sense, I will not go level by level, but I will go depth by depth. What does this mean? I will start from one. I will move to left or right. Either way I can do, but generally first left is traversed. So we will go to two first, and then three, and then we will arrive at our first path, which is one, two, three, and then we'll have to go back to one, and then again do a depth first into the right subtree, and that will lead us to the second path, which is one, two, three. Okay, and how do we do this? So we realize this fact that we have uh, we we conclude this fact that what do we what does this condition that I have arrived at the end of a path means? What are the characteristics shown by this particular scenario? So I know that when I reach some sort of a null pointer, when I reach some sort of end, so a leaf node is nothing but something having uh, no left or right um, subtrees, or it points to null basically. So what we have to look for is null pointers. We have to look for the tree path ending. We have to look for leaf nodes. So the algorithm will be based around null pointers, in the sense that if I arrive at a point where I see no left subtree and no right subtree, it simply means that I have arrived at a leaf node, and all I have to do is just add that current path to the answer string. And there is a second scenario, and there is third scenario. So there can be possibilities where I can have two subtrees present, but we are not concerned about that, because that simply means that we are still in transition, we are still traversing. But what do we have to look for when we have to do some sort of processing? We have to look for null pointers on our way. So whenever I reach a null pointer, I will have to do something about it. Okay. So say I encounter two null points, two null pointers. That simply means that I have arrived at the end, and I can just add that current value to the ongoing path, and just add that to the answer string. But there are two other cases where the left is present or right is present. So if either of them is present, that simply means that this is not something where I stop my traversal, or when I push my path. This is not that point. That point only arrives when both left and right are pointing to null. So what do I do at such a point where one of uh, the subtrees, one of the children, um, is null? So you take the one which is there, you take the value of that child, and you add it to the path, the ongoing path, plus you add that arrow, or whatever the question demands. In this particular case, we are expected to add an arrow, so we'll add an arrow at that point. We will not add an arrow when we will be pushing, and we will simply just add the value uh, of the leaf node. But in this particular case, we will add the value and add an arrow also. So if I do a dry run on this particular case, on these two particular cases, what I will do, I will come here. This is the root. I check whether this root is present or not. This is present. So what I will do is I will create. Okay, this is not dependent on whether the root is present or not. Either way, we will have to turn an array, an answer array. So this is like my answer array. Now, what do I pass to my helper function? And why do I need a helper function? Because we will have to keep track of current path. We will also have to keep track of the answer vector. Now we can declare the answer vector as a global variable, but we cannot do the same for path, because when we are moving recursively, at each point the path will have a certain value, and that that path will be very crucial, because it will only include the path till that point. And if we keep a global path variable, uh, we will not be able to correctly push paths. So we will have to um, keep it on the go and not take it as reference. So this is the root. I come here, I send my answer vector, I send my current path, which is nothing but empty string, and then I do my uh, helper function processing. So what does the helper function will contain? So it will contain three conditions. First of all, are the children null? So in this case, the children are not null. So do we have left child? Yes, we do have left child. So what we will do, we will just add the face value of this, which is 2, and we will add an arrow, and this will be my path. The path at this point will be 2 arrow, and not this 2 and arrow. Okay, and not 2 and arrow, but like 1 and arrow, because the current, so I was here, the current um, for this will be 1 and arrow, and I will pass from here. I will again recursively call the left one first, and I will send the root as root pointing to left. So this will become the root now for the function, and the path it will have is one arrow. And now the next if condition at this point was whether right is there or not, but we will not go there because this is a depth first search, and we will finish the depth first and then move on to the second children or child. So now since we are here, we will again do the three conditions. First condition, are the children null? No, children are not null. So do we have left child? Yes, we do have left child. What do? You simply add your current face value and you add an arrow, and you again do the same thing that you did previously. You send root pointing to left. So 5 becomes the new root in the next recursive function call. And in here, you check the same three things. First, do we have null pointers left and right? Yes, we do have. Now, what we will do, we will just add the current value, which is 5 in this case. So 1, 2, and 5, and we will not add an arrow here, but we will just push this thing in here. So this will go to this vector 1, 2, 5. Now the second condition at this level was, do we have a left? No, we do not have a left child. The third condition was, do we have a right child? We do not have a right child. So this will not do anything, and the call will come back to previous recursive function, which will have the second condition, the third condition being checked. Do we have a write? No, we do not have a write. So this will do nothing again. So the recursive call will go back here, and here also we did the left thing, and the first thing was also checked, and the second thing was also checked. Now the third thing will be checked. Do we have a write? Yes, we do have a write. So this will call another function, and in this case, the path. Now this is why I said that path cannot be a global variable, because in this case the path is one arrow, and the root will become 3 now, and we will again check the three conditions. Do we have null on both sides? Yes, we do have null on both sides. So what we will do, the current path, which is one arrow for this case particularly, because this comes from the first root, uh, this will be the path, and you will add the current value, which is 3. And since it has like null on both sides, this path will be pushed to the answer string. So this is one arrow 3, and now the second and third conditions will also be checked, but since we do not have left or right child in this particular case, we will not do anything, and this will go back. Now the first condition is checked on on this level. First condition is checked, second condition is checked, and the third condition is also checked. So hence we have arrived at the end of our recursive calls, and this is the answer that we will return. Right. Now coming to this case, we will initialize an answer vector, and we will check the same three things. First, do we have a left child? Sorry, first will be, do we have null on both left and right? Yes, we have null on both left and right. So since we have null on left and right child, the second and third conditions will be false, and they will not go in the if loop, because uh, neither left child is present nor the right one. So what will happen here? We will not add any arrow, just the current value, which is 1, and the path will become 1 and no arrow. And since both the children are null, are pointing to null, not children, but this root is pointing to null on both sides. What you will do is you will just push this path string into the answer. And since second and third conditions are false, the if conditions uh, will not be considered, and this function ends here only, and we will return this. So as you can see, in this case the answer is 1, in this case 1 to 5 and 3, which was like intuitive, but now you know how to do this in a DFS fashion. So first of all, let's initialize the vector. We can do this globally also, but I am doing here only, and I'll pass um, it with my helper function only. So let's call it answer, and now I'll just check if root is present or not. Now since the root is present, we can call a helper function, and it will have the root, the current path, which is empty, and the answer string or the answer vector. And after the processing is done, we will just return the answer vector. Now the answer vector, so let's call the helper function, and let's add these two functions. The path string will be empty for now, and this will not be passed by reference, because at every level the path is sort of different. um, but the answer vector will be passed by reference, because we need to um, make this consistent throughout all the calls. So yeah, now the first condition that we had was, are both the children null? So if root of left does not exist and root of root to right, which is right children node, does not exist, what do? You simply push into this vector the path after adding the current value. So answer dot, since it is a string, we will have to convert the values into string because they are integers, as you can see over here. Now push back current value. Sorry, the first the path will be there, path, and let's convert it to string. The value, we will add the value. Um, the value is root value, and yeah, this is my first condition. The second condition will be if root, if the left children exists, what will happen? We will simply add the current value and an arrow uh, to the path, and we will call the function for left children. So helper is again called with the root as the left children, and the path will become path plus um, to string. The value will be the current value and an arrow also. So an arrow. Okay. The same thing will happen for the right subtree. So let us copy paste. If the right children or the child exists, what you will do, you will pass the right as the root. You will add the current node's value and just add an arrow, and this should give you the answer. Right? Should not be an issue. I don't think I left any issue. Okay, so there is an issue. The issue is helper. Uh, helper is not declared. Root. Okay, so we'll also have to pass the answer vector. Right, sorry. So answer vector will also have to be. So this was not able to identify the function. Okay, so it is accepted. Let's run this. Yep, this works fine. If we analyze the, okay, we do not, we cannot. Okay. Now, let's look at the time complexity for this one. So, from my understanding, as we saw that we are moving to um, each node, let's say once. Although we are like going back to previous calls, but we are not like explicitly. So what is happening is we are going at one point and then we are going uh, to another function call. So we are like technically traversing all the nodes once. So the time complexity will be of n, and the space complexity will be of h being the height of the longest uh, node to leaf node distance. And in the case of skewed, as we have discussed earlier also, of n, because you are basically traversing through all the nodes. um, so the maximum space required will be of in the of n complexity zone. Yeah, so this was it for this video.